All right, in this video, we are going to study the notion of limit, which is a very important notion in mathematics, especially important in understanding the derivative, because as we saw on the previous lecture slide, the derivative is defined as the limit of the rate of change. So in order to better understand the derivative, we have to enhance understanding about the limit. So in this video, I'm going to talk about several properties of the limit and how to evaluate the limit and when limit exists. So I'm going to talk about several things about the limit. So this video is all about the limit. So I highly suspect you guys have seen this notation, say in high school or in other classes at the university. Just to remind you of this notation, so if we have a function g of v and we say the limit of g of v as v approaches number n is equal to L, if as v gets closer and closer to number n, function's value is very close to number L. Okay, so that is the basic idea of the limit. So this situation is described by this figure on the right. So if v approaches number n this way, okay, then we can see if we regard this curve as the graph of the function, then we can see the graph is heading toward this point, and whose y-coordinate is given by L, that is the limit value. So we can see the function is approaching number L as v approaches number n. Okay. And alternatively, we can write this as in this way. So as v approaches n, function approaches L. Okay. So either this way or this way, we can describe this kind of situation. So if we take a look at the diagram again, you may be able to notice that there are two ways to approach number n. So we may let v gradually increase to number n. So to get to this point number n. So v is approaching number n from the left, okay? Or we gradually decrease value of v to number n. So now v is approaching n from the right, like this way. Okay, so there are two ways to get to number n. We may increase or decrease the value of v. So depending on the direction, we can define two one-sided limits, as we can see on the next slide. So the basic idea of one-sided limits is v can approach number n from the left or from the right. Okay. So if v approaches number n from the right, we call that limit as the right-hand limit. So right-hand limit. And to distinguish from the normal limit, we put the positive sign here. Okay. So the right-hand limit of function g of v is the limit of the function as v approaches n plus. Okay, so here positive sign highlights the direction of v. So now v is approaching number n from the right, this way. Okay, or in this situation, v is decreasing to number n. So we can use a downward arrow to describe the right-hand limit. Okay, so either plus sign or downward arrow that indicate the right-hand limit of the function. And we can think of the opposite direction. So now v increasing number n. So v increases in value approaching number n. That's going to be our left-hand limit. Left-hand limit. So instead of a positive sign, we use a negative sign to denote the left-hand limit. So limit of function g of v as v approaches n minus. This negative sign highlights the direction of v. So now v is approaching number n from the left. Okay, and in this direction, v is increasing to number n. So we may use the upward arrow. Okay. So to denote the left-hand limit, so limit of g of v, v is increasing to number n. That is the another notation of the left-hand limit. Okay, so in these two figures, the left-hand limit and the right-hand limit of the function are different. And in the previous diagram, no matter what direction, as v approaches number n, function is heading toward the same point. So it has the same y coordinate. So the function is approaching the same value, L. So in this case, the left-hand limit and the right-hand limit of function are the same. But in these two examples, left-hand limit and right-hand limits are different. Okay. To express in symbols, let me call this function f of x, f of v. Okay. Function f of v, then right-hand limit of f of v, so as v approaches n plus, okay, so if we gradually decrease the value of v to get to number n, then we can see function is approaching L sub 2, okay, so the right-hand limit is L sub 2. On the other hand, the left-hand limit, so now we gradually increase the value of v to approach number n. Then the corresponding function is heading toward this point, whose y coordinate is L1. So we can see the left-hand limit. So as v approaches n minus of function f of v is L1, so which is different from L2. So at point n, we have two different one-sided limits. Okay. Even in this figure on the right, the two one-sided limit at point n are different. Okay, so if v approaches number n from the left, function is going down to negative infinity, and if v approaches number n from the right, and now function is skyrocketing, so it is diverging to positive infinity. So if I call this function, say, h of v, okay, and the left-hand limit of function h of v is negative infinity, but the right-hand limit, so v approaches n plus, is positive infinity. Okay. So whenever the limit has a infinite value, and we say the limit does not exist. Okay. So in this example, the limit takes a finite value of L2 or L1 depending on the direction. Then we say the at least one-sided limit exists. Okay, but the two one-sided limits are different. Okay, but in this example, h of v diverges either to negative infinity or to positive infinity. So the limit value takes an infinite value, then we say the limit does not exist. Okay. So now let me talk about the conditions under which the limit exists. Okay. So given a function y equals f of x, if the two one-sided limits exist, so take a finite value, and they are equal to each other, so we have a function f of x, and we examine the limit of the function as x approaches a from the right, or x approaches a from the left. So this right-hand limit and the left-hand limit are equal to number L. Okay, so it takes a finite value. So L is a finite, less than positive infinity, or larger than negative infinity. Okay, so two one-sided limits exist and equal to each other. Then we say the normal limit, so limit of a function as x approaches a, exists and equal to the common value of the one-sided limits. So it is equal to L. All right, so the existence of a limit requires three conditions. First, a right-hand limit must exist, and the second condition requires left-hand limit must exist, and the third condition requires these two limits be equal to each other. Right? So if these three conditions are satisfied, and we say the normal limit, limit of f of x as x approaches number a, exists. Okay. So in order to understand these three conditions, let me do this example. So here we have a one function whose graph is displayed in this diagram. And let me call this function f of x, and we are asked to evaluate the following limits. Okay, so now in the first question, the limit of a function as x approaches -4 from the right. Okay, so the situation is x approaches -4 from the right. Okay, then we can say the function is approaching this point, this empty circle. Okay, whose y coordinate is 2. So the limit value, the right-hand limit of the function at -4 is going to be 2. Okay. And the second, so if we think about the left-hand limit at the same point, if x approaches -4 from the left and still function is approaching the same empty circle, so the limit value is also 2. So at -4, left-hand limit, right-hand limit, both exist, and they are equal to each other. So we can say the limit of this function, normal limit of this function at -4 exists, okay? And whose limit value is going to be 2. And the second problem, now x approaching 1 from the left, okay? So 1 is right here. So x is approaching this number 1 from the left, okay? And then function is heading toward this circle, this point, 1, 4, whose y coordinate is 4. So the left-hand limit at number 1 is going to be 4. Okay. On the other hand, if we change the direction, so we let x approach number 1 from the right, okay? Then the function is getting close to this point, this empty circle, whose y coordinate is -2. So we can see the right-hand limit of the function at 1 is -2. All right, so although two one-sided limits exist, they take a finite value. They are different. So we can see that limit of function as x tends to 1 does not exist. Because two one-sided limits turn out to be different. Now we examine function's limit at number 6. So x increases to number 6 from the left, right? So that is a left-hand limit. We have a negative sign here. So the limit of a function at 6, then, as x approaches number 6 from the left, then function is approaching this circle, 6, 5. So we can see the left-hand limit is equal to 5. And in order to evaluate the normal limit at number 6, we have to examine the right-hand limit. So now x is decreasing to number 6. The function's graph is heading toward the same empty circle. So the right-hand limit is also number 5. So the right-hand limit, left-hand limit exist, and they are equal to each other. So we can say the limit of the function as x approaches number 6 is going to be 5. Okay, so that's the way to So that's the way to see when limit exists. Once again, these conditions are quite important. So for limit to exist, two one-sided limits must exist at that point, and they must take the same value. So if we examine the previous example, previous exercise, we have several empty circles, three empty circles on the graph. So at this point, so at -4, we have an empty circle, meaning that this function is not defined at -4. And still we can evaluate the limit because a limit tells us the approximate value. So although function is not defined, function may approach the same value from the left and from the right, then the limit value does exist. Okay. But here the function is disconnected. Okay. So it has a jump downward to -2 from 4. So jumps to -2, right? Then left-hand limit and the right-hand limit will be different. Okay. And at this point number 6, we have an empty circle. So the function, but is defined at this number 6, and the function's value is not, number 5, but number 2 at number 6, right? So limit value exists, that is number 5 at the point of 6, right? But the function's value is 2. So we can see that limit of f of x as x approaches 6 is 5, but that is not equal to function's exact value at that point, number 6, because that is a number 2. All right, so the previous example suggests that limit may exist even at a point where the function is not defined. So even at a point outside of the domain, the function's value, the function's limit may exist. Okay. So with that point in mind, now let's evaluate the following limits. Okay. So here we have three rational functions, and whenever we encounter rational functions, we should be careful about the denominator. So we have to check whether denominator is equal to 0 or not. Okay. So in the first rational function, we have x squared minus 2x, and now we let x approach number 2. So at 2, denominator is going to be 0, right? Still, there is a possibility that the limit of this function exists at that point. But for this example, as x approaches 2, the numerator is going to, so numerator approaching 4 plus 8 plus 12. So that is a non-zero number, 24. But the denominator is approaching 0, right? So we can see that function's value will be very close to 24 over 0. That is a really large number, because when x is getting smaller and smaller, we have to divide 24 by a very small number, a very infinitesimal number. So that is going to be infinity. Okay. But if x approaches 2 from the left, we can see that x squared minus 2x is approaching 0, but that remains negative. So it will be a very tiny number, but whose sign is a negative. So 24 divided by a very tiny negative number, so it's going to be negative infinity. So let me call this function f of x. Then the left-hand limit, f of x is going to be negative infinity. But if x approaches number 2 from the right, so x is decreasing to number 2. So that means f is approaching number 2, so it remains larger than number 2. So x squared minus 2x will be very tiny positive number. So now we divide the number 24 by very tiny small positive number. That will be positive infinity. So x approaches 2 plus, the limit of this function is going to be positive infinity. Okay. So the limit of this function at number 2 does not exist because it either diverges, so it diverges to either negative infinity or positive infinity. Okay. Now let's examine the second example. Now we let x approach number 7, and we want to see the limit of this function. Okay. Once again, as x at 7, this rational function is undefined because a denominator comes down to 0. But we can factor the numerator. So the expression on the numerator is factorable. X plus 8 times x minus 7. Okay. So before taking the limit, we can cancel out these two, x minus 7. So the function is equal to x plus 8 whenever x is not equal to 7. When x is not equal to 7. Okay. So this is the limit. So the limit notation indicates the approximate value. So x is not exactly number 7, but this describes a situation where x is very close to number 7. Okay. So for this reason, we can cancel off these two x minus 7 from the top and bottom. Okay. Whenever x is not exactly number 7, the function boils down to x plus 8. Okay. Now we take the limit as x goes to 7, then we can see that x plus 8 is approaching 15. So the limit value is going to be 15. All right, and then one more example now, x grows very large, so x goes to positive infinity, and 2x plus 5 over x plus 1. So to see this, we can divide top and bottom by x. Okay, then 2x plus 5 becomes 2 plus 5 over x, and the bottom, x becomes 1, and 1 becomes 1 over x. I just divide top and bottom, both sides, by x. Okay, then now we let x grow large. Okay, so x grows large. As x grows large, 5 over x, we divide a finite number by infinite number, then we can see that 5 over x goes to 0. And 1 over x also goes to 0. Okay, so these two fractions will be a very tiny number. So we can see this function is approaching 2 over 1, that is 2. And we have several other techniques when evaluating the limit at infinity. I'm going to talk about a little bit more about this after we talk about the derivative and after we learn several rules of differentiation. There is a very nice technique can be used to evaluate the limit at infinity. The so-called L'Hopital rule. I'm going to talk about that. All right, so the limit value of this function. So the limit of this function as x grows large to positive infinity is 2. And here I adopted the way of dividing top and bottom by x and use the fact that dividing finite value by large number is very close to 0. So I can cancel off these two expressions to get the limit value 2. All right, and then we have several limit properties. So to explain, suppose that both functions f of x and g of x have finite limits at number a. Okay, so the limit of function f of x as x approaches a, and the limit of a function g of x as x approaches a, both exist. Okay, then we have the following properties. First, whenever we have a scalar multiple, and we can pull it out. Okay, so a constant c can be factorable. So limit of c times f of x is the same as c times the limit of the function. Okay, and the limit of the sum of two functions, f of x plus g of x, will be the limit, or will be the sum of the limits. Okay, so limit of the sum is sum of the limits. So limit of f of x as x is going to a plus or minus limit of g of x as x approaches a. Okay, so the limit of sum or the limit of difference is going to be sum of limits or difference between limits. Okay, and the limit of the product is going to be the product of limits. Okay, so this is equal to limit of f of x times limit of g of x. Okay, and as x approaches a. And the limit of division is going to be so division of the limits. So limit of f of x divided by limit of g of x. Okay, so but one thing we have to be careful, so we should be careful whenever we encounter rational function. We have to make sure limit of g of x must exist. So it should be non-zero number. So whenever, only if limit of g of x as x approaches a is a non-zero number. Okay, if that is a zero number and this so this law does not hold any longer. And finally, limit of function, so f of x raised to the power number n, then we can put the limit inside. Okay, so that is going to be limit of f of x and raised to the power number n. Okay, so we can switch the order. We can first raise the power to number n and then take the limit, or we can take the limit first and raise to the power number n. Okay, and we end up with the same value. So the order of taking limit and raising the power, so these two orders can be switched whenever we want. So using these properties, we can evaluate the several polynomials or rational functions. So let me do just a few number of exercises here. Let me first do the second exercise. Okay, so we have a one polynomial function of variable y, and we are about to evaluate the limit of this polynomial as y approaches 1. Okay, then 6y to the fourth, because a constant 6 can be factored out, and y to the power fourth, we can first take the limit of y and then raise to the power number 4, that is a number 6. Okay, so this guy approaches number 6, and likewise negative 7y cubed is approaching number negative 7. 12y constant can be factored out, and y is approaching number 1. So 12y is approaching number 12. 25 is a constant, so independent of y, is fixed by constant. So if we add this up, then we have 37 minus 7, 36. I guess, okay. All right, and for this one, now we have two functions of t, and we divide one function by the other. So t squared plus 6, as t approaches 0, the limit exists. That is number 6. and t squared minus 3, the limit of this function as t approaches 0, also exists. So by the fourth row, division is going to be the limits of division. So that's going to be negative 2. All right, and then let me do this one. Okay. So now the limit of function of h as h goes to 0. Now we have a h on the bottom. And 2 plus h cubed minus 8. So yeah, let me do this. So 2 plus h cubed. Yeah, I'm not sure if you guys remember this formula. We have a plus b cubed. And there is a nice formula for, the how to expand this expression. So it's going, I think you guys know that a plus b squared and missed. So the way to expand this is a squared plus 2ab plus b squared. And for the power 3, the expansion is going to be a cubed plus 3ab squared and 3a squared b plus b cubed. Okay. Yeah, I don't think you guys have to remember this because whenever you forgot this formula, you can just Google, and in Wikipedia you can find the right formula. So I don't think we have to remember this, but in order to solve this problem, so in order to evaluate the limit of this function, we need this formula. All right. So 2 plus h cubed So employing this formula is going to be 8 plus 3 times 2 times h squared and 3 times 4 times 8h and h cubed. So a plus 6h squared 12h plus h cubed. Okay, and we take away number 8, so this number 8 goes away. So we are left with these h terms. And then we divide number h. We divide by variable h, because although h goes to 0, that is the limit, meaning that h is not equal to 0, but h is some number very close to 0. Okay, so that allows us to divide this expression by h to get 6h plus 12 plus h squared. Okay. After dividing by h, 6h squared becomes 6h, 12h becomes 12, and h cubed becomes h squared. We can just take one away from one away from each power, so we get this expression. Now we take the limit as h goes to 0, then 6h goes to 0, and 12, that is a constant, and h squared going to 0, so we have just a 12. Let me do one more exercise. So the limit of this expression, so 1 over 7 minus 1 over x divided by x minus 7. Okay. So now the technique we are going to use for evaluation of this limit is to make a common denominator. So whenever we have two rational functions, so 1 over 7 minus 1 over x, and we can put them together to find out the common denominator, that is 7 times x. Okay, so we change the numerator to 7 times x. So for 7, we need to multiply top and bottom by x. So 1 becomes x. And for 7, now we need to multiply both top and bottom by 7. So 1 becomes 7. Okay. In general, if we have 1 over a minus 1 over b, then if we put them together, then the common denominator is a times b, and so 1 over a becomes b over a times b. 1 over b becomes a over a times b. Okay. So after rewriting the numerator to find out, after finding out the common denominator, we can put together these two fractions on the top. So after dividing by x minus 7, so x minus 7 over 7x and divided by x minus 7. So now we can, we can cancel off these two x minus 7 from the top and from the bottom. Okay, so we are left with just 1 over 7x. Okay, now we can take the limit as x goes to 7. 1 over 7x is approaching 1 over 49. Okay, so this is here 1 over 49. Right? So using the same technique, I think you can evaluate this the limit of this function as well. All right. So this is the end of the second video. Hope you guys enjoyed that, and hope you guys now had a better understanding about the limit. And then I will keep recording lecture video for the next topic, and I'll see you in the next video.